Okay, so number 12, we have for each one of these problems 3 questions. So I think I'm going to use a table to write down my answers. So for number 12, each of these problems involves limits. Some of them are one-sided limits, left-hand limits and right-hand limits, and others are two-sided limits. You need to pay attention to the little symbol, if there is one, sitting above the value that x is approaching. So in this very first problem, you can see that x is approaching -5, and then there's this minus sign. That minus sign indicates that you're thinking about what's happening to the function as x approaches -5 from the left. So that's a left-handed limit. Likewise, in this problem here, you see this little plus. That plus indicates that you're thinking about what is happening to the value of the function as x approaches -5 from the right. In this third one here, there is no plus or minus, and that indicates that you're looking at a two-sided limit. The thing about two-sided limits is they are very often not defined. They're only defined if the left and the right hand limits, that is these two guys here, are equal, if they're the same number. So for example, if this guy is 7 and this guy is also 7, then the two-sided limit will also be 7. However, if this first guy is 4 and this second guy is 3, then the two-sided limit will simply not exist. Okay, so let's go through these. This is the limit as x approaches -5 from the left. That's what this minus sign here means. So what we're going to do is we're going to look at the graph and we're going to ask what is happening to the y values, the y coordinates of the graph as x, the x coordinate, is approaching -5 from the left. So here's -5. We're approaching -5 from the left. That means from over here. And we're getting closer and closer to -5 from the left. And as that occurs, we're asking what's happening to the corresponding y values. The y values are getting closer and closer to +5. So that first limit is 5. This second limit, it's the limit as x approaches -5, but because of that plus sign, it's from the right. So I'm going to get closer and closer to -5, but now from the right. And I'm going to ask what's happening to the y values of the function as that occurs. Well, the y values are just getting bigger and bigger in the negative direction, -8, -9, -10. So I don't think that the y values are converging or settling down on any particular number. Rather, the y values are becoming larger and larger negative numbers. So the y values are approaching -infinity. What we would write down as an answer to this question is actually DNE, which stands for does not exist, and then in parentheses, -infinity. Just a quick note on why we say DNE, -infinity, and not just -infinity. Limits only exist when the y values are approaching a number, like a particular number, like 7 or 17. -infinity is not a number, okay? So if the values are approaching some kind of infinity, that limit does not exist. But we like to say, in responding to this kind of question, if a limit fails to exist, we often like to say why. So we'll say DNE, which means does not exist, and then in parentheses, we're saying it doesn't exist because the y values are approaching -infinity. The reason that the limit fails to exist is really sitting in the parentheses there. And then finally, here, this is the two-sided limit because there's no plus or minus above the -5. That guy is only defined if the left and the right-hand limits are the same, and they are not in this case, right? So I can quickly just write this guy does not exist, okay? And you don't need to write a reason or anything when there's like a mismatch of the left and the right-hand limits. It's really just for the infinity case that we expect you to provide a reason like that. Okay, B. Okay, so now we're doing B. So we're done with this guy. B. Limit as x approaches 0 from the left. So we're asking what's happening to the y values of the function as x approaches 0 from the left. Looks like it's approaching 3. Great. Okay. How about the limit as x approaches 0 from the right? Well, if x approaches 0 from the right, the y values are also approaching 3. So cool. So this is also 3. Two-sided limit. Well, that guy only exists if the left and right hand limits are the same, and in this case they are. So the two-sided limit does exist, and it's just also equal to 3. By the way, you might notice there's a hole in the graph here. What that means is that this function is not defined at 0. So if I asked you, hey, what's f of 0? You would have to say undefined, or it does not exist. The function doesn't have a value at 0. But notice that these three limits don't care about that. They don't care about that at all. This is a very important thing to understand about limits. They don't care about what is happening at the point. These three limits don't care about what's happening at 0. They only care about what's happening as you approach 0, as you get close to it. The cute way of describing this is to say that limits only care about the journey, not the destination. Okay, so that one's done. C. Limit as x approaches 2 from the left. So here's 2. I'm approaching it from the left. What's happening to the y values? They're going to negative infinity. Great. So I'm going to say dne negative infinity. Okay. 2 from the right. As I approach 2 from the right, what's happening? Again, the y values are approaching negative infinity. So I'm going to say dne negative infinity. And now the two-sided limit. Well, the left and the right. Well, first of all, look. This limit doesn't exist. Okay. You might be tempted into thinking that it does exist or something because the left and right hand limits sort of match, but they don't. They're not both equal to numbers. Okay, they're not both equal to numbers. That's kind of the point. If one side fails to exist, then the two-sided limit definitely won't exist. So what we're going to say for this guy is dne, and then in parentheses, negative infinity. Because it's going to negative infinity on the left and the right. If it were positive infinity on the left and to the right, then I would say for the two-sided limit, dne plus infinity. If it were negative infinity on one side and positive on another one, we would typically write dne plus minus infinity, like to indicate that it's positive on one side and negative on the other. But in this case, it's minus on both. So we're just going to say minus infinity. Okay, that one's done. D, limit as x approaches 3 from the left. As x approaches 3 from the left, the y values are approaching 2. There's actually nothing interesting happening like at this point, really. So yeah, that's 2. As you approach 3 from the right, what are the y values approaching? Well, also 2. Cool. And the two-sided limit. Does the two-sided limit exist? Yeah, because the left and the right-hand limits both exist, and they match. They're 2, right? So this guy is also just 2. Cool. So that's D. Moving on to E. Limit as x approaches 8 from the left. As x approaches 8 from the left, the y values are approaching 7. So that's 7. As x approaches 8 from the right, the y values are approaching 9. So that's 9. The two-sided limit does not exist because the left and right-hand limits are different. So that's E. Finally, F, limit as x approaches negative infinity. That is asking what is happening to the value of the function as x becomes a very, very large negative number. Notice it's x that's going to negative infinity here. Sometimes people look at this limit and their eyes are drawn to like these portions of the graph. That's not correct, okay? In these portions of the graph, it's not x that's going to negative infinity, it's the y coordinate that's going to negative infinity. So for this limit here, where it says limit as x goes to negative infinity, you want to be thinking about the x coordinate of the graph going to negative infinity. That means you're going way out to the left, and you're asking what's happening to the y values as you do that. As I go way off to the left, what's happening to the y values? I think the y values are just getting bigger and bigger. Like, I don't think they're settling down on anything. So I think they're approaching infinity. So you could say dne infinity. Same question now, but for x going to positive infinity. So we're going to ask what's happening to the y values as x becomes a very, very large positive number. Well, as x becomes a very large positive number, I go way out here. It looks like the y values have settled down on the number 9. So I think the answer is 9. Voila, that's the last one. Here in this next page, we have this great flow chart. I'm not going to go over it right now. I just want to draw your attention to it. A lot of times after learning all the stuff there is to know about limits, infinite limits, non-infinite limits, all this other stuff, students get kind of confused. This thing here sort of summarizes all of it. So yeah, I'll come back to this. Okay, so now we're going to move on to algebraic limits, and so I guess we are going to use this flowchart right away. So unlike the previous problems, here we're evaluating limits algebraically. That is to say, we don't have a graph of the function. Instead, we just have a formula, and we're trying to evaluate these limits. So what do? The procedure is outlined here. So there's kind of two things that can occur, broadly speaking. Your x value could be approaching a number c, like it is, I think, in all of the exercises on this page right here. X is approaching 4. Natural log of 5, that's still a number, even though it's kind of a stupid number. 0, 0, 3. X is approaching a number in all of these problems. On the other hand, in the next page, you'll see that x is approaching infinity or negative infinity. Those are two different kinds of problems which require two totally different approaches, and that's why you're seeing these two cases at the beginning. If it's limit as x approaches positive or negative infinity, you do blah, blah, blah. On the other hand, if x is approaching a number c, then you follow this process here. And that's what we're going to be doing for this page. So as x approaches a number c, to find the value of that limit, what you're going to do is you're just going to plug in c. Like you're just going to plug that number in to the function and see what happens. And what happens next tells you what to do. So this is the flow chart. The easiest possible scenario is you plug in the number c and you get a well-defined actual number, like 7 or 6/5 or something. If you plug in c and you get an actual well-defined number, like no zeros and denominators, you're done. That's the value of the limit. So you're all set. That will almost never happen. It's so easy, like we won't ask you to do that very often. Instead, what will most often happen is you'll get 0/0. Okay, 0/0 simply means that you have to simplify or rewrite the function. And how you simplify it just depends upon the problem. Could be factoring the top and bottom of a fraction and canceling common factors, or it could be like multiplying by the conjugate or something. But at any rate, you need to simplify the function, and then you go back to this step and try again, okay? And try plugging the number in again. And hopefully this time when you plug in the number c, you don't get 0/0 again. If you do, then you have to simplify it even more. The last option is if you plug in c, you might get a non-zero number over 0, like 5/0 or 7/0. If that occurs, then you have a vertical asymptote, and you're obligated to figure out whether the function is approaching positive or negative infinity on either side of the vertical asymptote. I'll talk about that in more detail when we get into the problems. So let's get started on these guys here. Okay, so with that explanation, 13. So I'm looking at this guy right here. First step, what do? I plug in c. So I plug in 4 into this function. If I plug in 4, I get 4 squared minus 6 times 4 plus 8 over 4 minus 4. So that's 16 minus 24 plus 8 over 0. I think that's 0/0. In my flowchart, what does that mean? If I get 0/0, that means I need to simplify and try again. So I'm going to simplify this function. I think what I can do is I can rewrite this guy and factor it. So I'm going to factor the top. The top factors as I need a pair of numbers that multiply to 8, add up to -6. That's -4 and -2. And then the x minus 4's cancel, and I get just limit as x approaches 4, x minus 2. Notice I'm copying limit as x approaches 4 each and every time. That's important. Okay, so I've simplified the function. Now So now that I've simplified the function, I go back to here, I plug in c again. I just try plugging the number in again. Hopefully this time I get an actual number. If I plug in 4 now, I get 4 minus 2, which is 2. That's an actual number, so that's the value of the limit. 14. Limit as x approaches e. E is that special number, right? It's like 2 point whatever. It's the base of the natural logarithm. Our first step is we're going to plug that number in. Of course, I get ln of e. Is that a number? Yes, it is. It's 1, right? That's the power of e, which gives you e. That's 1. So 1 is an actual number. So that's the value of the limit. We're done. 15. Limit as x approaches natural log of 5 e to the x. ln 5 is a funny number, but that's still a number. So I'm going to plug that in. I'm going to get e to the ln 5. Is that an actual number? Yeah, it is. You might remember it's just 5. The exponential e and the natural logarithm, they kind of cancel each other, and you're just left with the thing on the inside of the log. That's 5. 16. Okay, limit as x approaches 0. If I plug 0 into this guy, I can tell right away that I get 0 over 0. I can see that in my head. So I know that I have to simplify this. So I'm going to simplify it by factoring out the common factor of x in the numerator, which leaves me with x squared plus 4. And then I can cancel the x's in the top and the bottom, which gives me just x squared plus 4. And if I plug 0 into that, I get 0 squared plus 4, which is 4. That's an actual number, so that's the value of the limit. 17. If I plug 3 into this, do I get 0 over 0? I definitely get 0 on the bottom. Do I get 0 in the top? 3 squared minus 6. I do. So I get 0 over 0, which means that I need to simplify. So I'm going to simplify by factoring. I'm going to factor the top and the bottom. The top factors as x minus 3 times x plus 1. And the denominator, you can pull out a common factor of 6, which leaves you with x minus 3. The x minus 3's cancel, and I'm just left with x plus 1 over 6. And if I plug 3 into that, then I get 3 plus 1 over 6, which is 4 over 6, which is 2/3. Okay, 18. If I plug 0 into that, do I get 0 over 0? I think I do, because 5 plus 0, quantity squared, minus 25 over 0. This is 5 squared, which is 25. So it's 25 minus 25. That's 0 over 0. So that means I need to simplify. How do you simplify this? I would start by multiplying out the expression in parentheses. Like, I would expand it. So that's 25 plus 10x plus x squared minus 25. And then I notice that this 25 here minus that 25 there, those 25s are going to cancel, so I'll just get rid of them. That leaves me with 10x plus x squared over x. If I plug 0 into this, you actually still get 0 over 0. That's fine. That just means we need to do more simplification. So what I can do is I can pull out the common factor of x in the numerator, which leaves me with x times 10 plus x over x. The x's cancel, and I'm left with just 10 plus x. If I plug 0 into that, I get an actual number, 10, so that's the limit. 19, if I plug in 2, do I get 0 over 0? Let me see, in the numerator I have 2 squared, which is 4, minus 4 times 2, which is 8, plus 4, that's 0 on top. And the bottom I get 2 squared, which is 4, plus 2 times 5, which is 10, minus 14. So I do get 0 over 0, which means I need to simplify. I'm going to simplify by factoring and canceling common factors. So the top factors as x minus 2 times x minus 2, and the bottom factors as x plus 7 times x minus 2. So those factors of x minus 2 cancel, and I'm left with x minus 2 over x plus 7. And if I plug 2 into that, I get 0 over 9, which is just 0, right? 0 over a non-zero number, that's just 0. So that's the value of the limit. 20, if I plug 2 into that, what do I get? I get 4 plus 10 minus 14. And on the bottom, I get 4 minus 8 plus 4. I think you get 0 over 0 again. Okay, so that means I need to simplify. So I'm going to factor everything. So if I factor the top, that's x plus 7 times x minus 2. On the bottom, that factors as x minus 2 times x minus 2. The x minus 2's cancel, and I'm left with x plus 7 over x minus 2. And if I plug 2 into that, then I get 9 over 0. Now this is very interesting because 9 over 0, that's a non-zero number over 0. That actually puts us in this situation right here, which means we have a vertical asymptote at c. So we have a vertical asymptote at 2. So I'll analyze that in a second, and I'll show you how to figure out whether the function is approaching positive or negative infinity on either side of the vertical asymptote. But I just want to point out really quickly that it's a common myth amongst students that if you get 0 over 0, that means you have a hole in the graph. That's not true. As you can see, in this case, we initially got 0 over 0, but upon further inspection, we saw that actually we have a vertical asymptote there. 0 over 0 doesn't really mean anything other than you need to do more investigation. You need to rewrite the function and try again. It could be a hole, it could be a vertical asymptote, or who knows what. So anyway, how do you determine what's going on? Because essentially, like, you know that this function has a vertical asymptote at 2, right? So maybe this is 2 right here, right? So you know that you've got this vertical asymptote here, but the question is, what is the graph doing as you approach 2 from either side? Is it going to positive infinity on the left? Is it going to negative infinity on the right? Or is it positive infinity on both? Or what's the story? How do you figure that out? It's pretty simple. All you need to do is pick a number close to 2 on the left, pick a number close to 2 on the right, and plug them in and see whether you get a positive or negative number as a result. So for example, the number just to the left of 2 that I might pick is 1.9 or 1.99. So plug 1.9 or 1.99 into the function. You should plug it into the factored version of the function. As a matter of fact, you can plug it into the simplified version of the function if you like. It doesn't make any difference though. I'll plug it into into the original one just to show you that it doesn't matter. It's also a better example if I do it that way. So I'm going to plug 1.9 into the function. Remember, my goal is to figure out, is the function going to positive infinity on this side or negative infinity on this side? What I'm interested in is, if I plug in 1.9, do I get a positive number as a result, which would put me up here? Or do I get a negative number as a result, which would put me down here? So I'm going to plug in 1.9. And, as I said, you can plug it into the simplified version, but I think we'll learn a little more if I plug it into the original unsimplified version of the function. So my goal here is to figure out, is this a positive or a negative number? You might feel intimidated. These numbers are going to be not very nice. You're not going to have a calculator for a problem like this. The thing is, though, you don't actually have to compute these numbers. All you have to do is keep track of the sign, like whether each factor is positive or negative, and you don't need a calculator for that. So this first factor, 1.9 plus 7, that's a positive number. I don't care what positive number it is. It's a positive number. This second factor, 1.9 minus 2, that's a negative number. So it's some positive number times some negative number. 1.9 minus 2, that's a negative number. 1.9 minus 2, that's another negative number. So in the numerator, you have a positive times a negative, which is a negative. And the bottom, you have a negative times a negative, which is a positive. Overall, we have a negative over a positive, which is negative. So that's going to be some negative number. I don't care what negative number it is exactly. I know that at 1.9, the value of the function is negative, So the graph is down here. That means that as x approaches 2 from the left, the graph is going to negative infinity. We're going down there. Okay, so now I have to repeat that analysis, but with a number from the right. So I'm going to plug in a number close to 2 on the right, like 2.1, just to show you, as I say, you can use the simplified version, right? So I'm going to plug in a number just to the right of 2, like right here, 2.1. If I plug that in, 2.1 plus 7 over 2.1 minus 2, what does that give you? Well, it's some positive number over some positive number. So the whole thing is going to be a positive number. So the graph is up here. That means the graph is going to positive infinity on that side. So that's what the graph looks like. That's what the vertical asymptote looks like at 2. What do we report as our answer? Like, what do we write down for our answer? Well, first of all, this limit doesn't exist. Limits only exist if the values are approaching a number, and infinity is not a number. So I'm going to say DNE, but we need to say how it fails to exist, right? And what's happening is it's positive infinity on one side and negative infinity on the other. The way that we report that is by writing plus minus infinity, okay? If it were infinity on both sides, then I would say just infinity. If it were negative infinity on both sides, I would say just minus infinity. Here it's both. 21, I'm going to plug in negative 3. So if I plug in negative 3, I get negative 18 minus 12 over negative 9 plus 9. That gives me negative 30 over 0. That is a non-zero number over 0. We are once again in this case right here, so that means we have a vertical asymptote, and we have to investigate what's going on. If you want more details about how this works, I did it in gruesome detail in the previous problem. Here, I'll do it very quickly. I'm going to work with the factored form. You should always work with the factored form, and you can do some factoring here. 6 times x minus 2 over 3 times x plus 3. You should always factor it before doing this like analysis of the positivity or negativity of the values. So I'm going to plug in a number just very close to negative 3 on the left, like negative 3.1. So if I plug in negative 3.1, I just need to keep track of the signs. This thing in parentheses, that's negative times 6, which is positive. So it's a positive times negative. So the numerator is negative. This guy here, negative 3.1 plus 3, that is also negative. Times 3 is still negative. So it's minus over minus, which is plus. So the function's approaching positive infinity on the left. And now if I plug in a number just to the right of negative 3, like negative 2.9, and keep track of the signs, that's 6 times some negative number over 3 times some positive number. The numerator is negative, the denominator is positive, so the whole thing's negative. So on the right, it's going to negative infinity, which means my final answer is DNE plus minus infinity. 22. If I plug in 0, I can see that I get 0 over 0. So I need to simplify this. A lot of people are going to have trouble with this one, I think. They usually do. This is a complex fraction, which means you have fractions inside of other fractions. Your goal, whenever you have a complex fraction, is to rewrite the complex fraction so that it is in the form a over b over c over d. In other words, one fraction divided by another fraction. Because once your complex fraction looks like this, you can use keep it, change it, flip it, or multiply by the reciprocal or whatever, and you sort of know what to do. This guy is not remotely in that form yet. We have to do a bunch of algebra to put it in that form, and you cannot do keep it, change it, flip it until you get it in that form. All right, so what to do? Well, for one thing, notice this guy here, that x, I want to make that a fraction. Like, I want that to be my c over d. That's very easy to make into a fraction. Just make it x over 1. Now it's a fraction. Cool. So that's my c over d. The numerator takes more work. It's 2 fractions, and I have to combine them. But to combine them, I need common denominators. So I'm going to multiply top and bottom of this fraction by this denominator, 3, and I'm going to multiply top and bottom of this fraction by this denominator, 3 plus x. So that gives me 3 over 3 times 3 plus x minus 3 plus x times 3 plus x. So far, so good. So notice I'm copying limit every single time. Now in the numerator, we're going to combine those two fractions. Okay, we keep the denominator, and we're going to put the numerators together. And this is where a lot of people are going to make a mistake. If you got the opposite of the correct answer, you probably made the mistake that I'm about to talk about. When you combine these two fractions, your new numerator, like the numerator here, is supposed to be this numerator minus this numerator. What a lot of people will do is they'll just write 3, which is this numerator, and then they'll write a minus sign, and then they'll write this numerator, 3 plus x. That is actually not quite right. Let me repeat what I said. We're trying to do this numerator minus this numerator. Here, I'm not really subtracting this numerator. The minus sign is only being applied to the 3. In other words, the minus sign is only being applied to the first term of this numerator, but I want this minus sign to be applied to the entire numerator here. I'm supposed to be subtracting the numerator, not just the first term of the numerator. So what I need parentheses around this guy to ensure that the minus sign actually is applied to the entire second numerator. So having done that, when I distribute the minus sign, I get 3 minus x over 3 times 3 plus x, which gives you limit as x approaches 0, x over 1, and the numerator I have negative x over 3 times 3 plus x. Now my complex fraction is finally in this form, one fraction divided by another, which means I can use keep it, change it, flip it. So I'm going to keep the first fraction, negative x over 3 times 3 plus x, the same, change the division to multiplication, and flip the denominator. Okay. So now multiplying those two fractions, multiplying across the top and the bottom, I get negative x over 3x times 3 plus x. If you plug 0 into that, you still get 0 over 0, which means that you need to simplify more. The last thing that you have to do is you have to cancel this x with this x. After you do that, then you should finally be done with all the algebra. So canceling those common factors, I have negative 1 over 3 times 3 plus x. And if you plug 0 into that, then you get negative 1 over 3 times 3 plus 0, which is just negative 1 over 9. Okay, so there we go. 23. Limit as x approaches 4 of root x minus 2 over x minus 2. If you plug 4 into this, you get 0 over 0. I'll save you the time. That means we need to simplify. How do you simplify? Conjugates. Conjugates. You need to multiply top and bottom by the conjugate of the square root expression. Whenever you need to simplify an expression involving square roots, there's a very strong chance, like a 85% chance, that you need to use this method, multiply top and bottom by the conjugate. The conjugate of an expression a minus b is a plus b, and vice versa. So conjugating an expression just means like changing the minus to a plus or changing the plus to a minus. So what I'm going to do is I'm going to take this expression and I'm going to, it's a fraction. It's a fraction, so I'm allowed to multiply top and bottom by whatever I want, as long as it's the same thing, top and bottom. I'm going to multiply top and bottom by the conjugate of the square root expression. So here's the square root expression. It's root x minus 2. I'm going to multiply top and bottom by the conjugate of that, which is root x plus 2. Okay, so root x plus 2. Now, the numerator, if you multiply this out, it will turn into something pretty nice. Because if you ever have an expression a minus b times its conjugate, a plus b, that always multiplies out as a squared minus b squared. The mixed terms, like the plus ab and the minus ab, they cancel, and you just get a squared minus b squared. I mean, like, you can do this manually, get a squared and like plus ab and then minus ab and then minus b squared, but the middle terms cancel. The middle terms cancel. That's what's going to happen here because we have an expression of that form. It's an expression times its conjugate. So you can skip all the intermediate steps and just say, I know how this is going to multiply out. It's going to be this guy squared, which is just x, minus this guy squared, which is just 4. Okay? The denominator you should not multiply out. Okay? The denominator you should not multiply out. Oh my god. You do not get 0 over 0. Oh yeah, you do. No, you don't. You don't get 0 over 0 on this problem. What am I talking about? What am I talking about? No. This is what happens. When you've done too many calculus problems, sometimes you just assume that you know what the problem is that you're looking at. Oi. That's fine. Yeah. If you plug 4 into that, you get root 4 minus 2 over 4 minus 2. That is not 0 over 0. That is 0 over 2, which is just 0. The end. I think the second problem is maybe more interesting. Yes. Yeah, this one is more interesting. 24 is more interesting. So it's in this one that we need to multiply by the conjugate. So if you plug 4 into this guy, you do get 0 over 0, which means we need to simplify. And whenever you see these square root expressions floating around, probably you need to multiply top and bottom by the conjugate. So I'm going to multiply by the conjugate of the square root expression. For more details, listen to what I said for number 23, even though that method wasn't appropriate. Like, I explained the method of multiplying by the conjugate in detail on number 23, even though that method wasn't the right method to use there. So if you want more details on exactly what I'm doing when I multiply by the conjugate here, just go ahead and watch my explanation of number 23, even though I was being stupid and you don't actually need the conjugate for that problem. Yeah, so multiply top and bottom by the conjugate of the square root expression. So that's multiplying top and bottom by square root of x plus 2. So in the denominator, you have an expression times its conjugate. You have something of the form a minus b times a plus b. And that always multiplies out very nicely. That will multiply out in the form a squared minus b squared. So it's going to be this guy squared, which is just x, minus this guy squared, which is just 4. However, the numerator you should not multiply out. You should leave it in factored form. Because if you do multiply it out, you will not get a nice expression. We got a nice expression when we multiplied out the denominator because it's in the form a minus b times a plus b. It's an expression times its conjugate. But the numerator is not of that form. The numerator is not of the form a minus b times a plus b. It's just two unrelated expressions being multiplied. If you multiply it out, it will just be a mess. And if you multiply it out, most importantly, you will miss the fact that there's a common factor of x minus 4, which can be canceled now, right? So basically, when you're doing these conjugate problems, make sure you only multiply out in the part of the fraction which involves the expression times its conjugate, right? Leave the other part of the fraction in factored form. So the x minus 4's cancel, and we just have root x plus 2. If I plug 4 into that, I get root 4 plus 2, which is 2 plus 2, which is 4. So now we move on to evaluating limits as x goes to infinity. These tend to be a little easier than the previous ones. So if you go back to the flow chart up here, we're sort of in this case here. If you're looking at a limit as x goes to positive or negative infinity, you need to decide which terms grow the fastest and which ones grow the slowest, and just delete the slower growing terms. I don't see it here in these notes, but I usually talk, when I teach this topic, I usually talk about something called the hierarchy of growth, which basically explains like which functions grow the fastest and which ones grow the slowest. So maybe I'll just go through that like here. Basically, the slowest growing functions are constants because they don't grow at all. But also things like cosine and sine, those functions don't really grow. They just oscillate up and down between positive and -1. After that, much, much faster than that guy are powers of x. So that includes obviously functions like x squared and x cubed, but it also includes things like square root of x, because square root of x is a power of x, like it's x to the 1/2. Within this family, the higher your power of x, the faster you grow. And then after that, we have exponentials, which are functions where the x is in the exponent. So stuff like 2 to the x, which is less than 3 to the x, which is less than 4 to the x. And basically, what I want to point out here is that all that matters when you're analyzing who grows the most quickly is this hierarchy. Coefficients don't matter. So if we look at number 25, for example, this one right here, I mean, obviously x cubed grows faster than x squared. That's kind of obvious. This one here, the 100 is meant to trick you, like, but no, it doesn't matter. Like in the hierarchy, x cubed grows faster than x squared. So I don't care if you slap a 100 in front of the x squared. X cubed, this guy will eventually catch up, essentially, to this guy. So here, this guy grows faster. Here, x squared to 2 to the x. 2 to the x is an exponential. That's in this family. The exponentials grow faster than the powers of x, so 2 to the x grows faster. 2 to the x or 3 to the x or 3 to the x, right? 3 to the x is higher in the hierarchy. Root x or 5 cube root of x. Well, to see that, I think you need to, like, rewrite. Square root of x is x to the 1/2 versus 5 cube root of x is like 5x to the 1/3. The 5 makes no difference. Like, coefficients don't matter. You might as well just ignore it. Who grows faster? This guy does, because 1/2 is bigger than 1/3. So like in this family of functions here, like, you know, root x, which is x to the 1/2, that grows faster than x to the 1/3, which is faster than x to the 1/4, etc. Finally, this one here, this doesn't come up too much. Natural logarithms, you'll notice I didn't even include logarithmic functions in this hierarchy explanation. Logarithms actually go here. Logs are slower than any power of x. Logarithms grow very, very slowly. Okay, so so natural log of x actually grows slower than this guy. So cube root of x grows faster than ln of x, so that's the guy that wins. So anyway, with that discussion about fast and slow functions out of the way, we can sort of now turn to analyzing these limits as x goes to infinity. So the logic behind these is basically that when x is going to infinity or negative infinity, all of the terms are, or most of them anyway, are getting really big. Like 3x squared is getting really big and 5x is getting really big. They're all getting really big. But some of them are getting really big a lot faster than others. So in this expression here in the numerator of the first problem, the x squared term grows faster than the x term. So for very large values of x, like x equals 1,000, 1,000,000, 1,000,000,000, for very large values of x, the 3x squared term is going to be so much larger than the 5x term that you can just ignore the 5x. And likewise, the 1, I mean, the 1's not growing at all. You can just ignore it. Just forget about it. So in the numerator, the fastest growing term is 3x squared. You keep that term and you just ignore the others because they're tiny by comparison. They're negligible. They can be ignored. Same analysis in the denominator tells you that 7x squared is the fastest growing term, and you can ignore these other guys. So what you're looking at here is really a simplified problem, right? You still need to think about the limit as x goes to infinity, but now the function's a lot simpler. It's just 3x squared over 7x squared. Well, you can simplify that, right? Like you just get 3 over 7. That's the value of the limit, the end. For b, a similar analysis tells you like which terms to ignore. So in the numerator, the faster growing term is the x cubed. So ignore this guy. In the denominator, the fastest growing term is x to the 4th. So ignore this guy. Don't be tricked by the coefficient. The coefficient doesn't matter. And of course that simplifies, not to a number, but to something that's easier to understand. It simplifies to 1 over x. So, you know, unlike the previous problem, it's not a number. You have to do a little more thinking to figure out what's going on. Well, you know, as x goes to infinity, you're looking at like 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. What's happening to that sequence of numbers? It's approaching which value? It's approaching which number? It's approaching 0. So that limit is 0. All right, that's generally what's going to happen when the denominator grows faster than the numerator. 26c, you know, once again, we're thinking about what are the fastest growing terms and the slowest growing terms and so on. In the numerator, x to the 5th versus 2 to the x. 2 to the x is an exponential. Like in the hierarchy of growth that I was talking about here, the exponential wins out. So that's the term we keep. Same thing in the denominator, 2 to the x wins. Well, 2 to the x over 2 to the x, those cancel. It's just 1. So voila. 26d. Here, there are no terms to eliminate. Like there's only one term in the top and one term in the bottom. So you sort of, and there's no like simplification that you can do. However, notice like the numerator is an exponential. E is like 2 point something. And the denominator is a power of x. And like I was saying before, exponentials grow faster than powers of x. So that means that for large values of x, the top is growing faster than the bottom. So for large values of x, the top is going to be a lot bigger than the bottom. And if you have a fraction where the numerator is much bigger than the bottom, the overall value of the fraction is going to be large. So the value of this fraction is getting bigger and bigger. It's approaching positive infinity because both the top and the bottom are positive. But you could say dne infinity because technically limits only exist if the function is approaching a number. Infinity is not a number, so it's good to say does not exist and then in parentheses infinity. Okay, e. Well, I think we need to think about which terms matter. It might be helpful to think about the exponents here. That root x is 2x to the 1/2. That cube root of x is x to the 1/3. 5 times x to the 1/4 minus x to the 1/2. So in the numerator, which terms grow fastest? I think it's this guy. Because 1/2 is bigger than 1/3. Right, so that exponent is bigger than this exponent. So yeah, the square root term grows faster. So I'll just forget about that guy. Likewise, here it's the 1/2 that's bigger than the 1/4. So this is the term that I'm going to keep. And the 5x to the 1/4 I'm going to delete. Notice though, the minus sign stays. Like when I delete this guy, the minus sign is still going to be there. This minus sign is attached to the term on the right, not the term on the left. So like it's still there. So the x to the 1/2s cancel, but you do still have a minus sign in the denominator. So it's like a 2 over -1, which is -2. Finally, 26f. Yeah, once again, I don't know, this seems pretty straightforward. If we just delete the slower growing terms, like that, forget about that guy, and forget about this guy, you're going to be left with just limit as x approaches infinity of 90 x to the 4th over, oh, and once again, that minus sign is still there, right? Watch out for that. That minus sign is attached to the term on the right. So, yeah, you can do a little more simplification. Like, you can cancel the x's. You get 90 over negative 3x, which I guess you could say is like negative 30 over x. What happens to the value of this expression as x gets really big? It goes to 0, right? Like the denominator is getting bigger and bigger, the numerator is staying the same, so that's 0.